Alright, I just, it's getting kind of close to Christmas when I'm doing this video, and if you don't celebrate Christmas, then happy holidays. Yeah, I just found out today it kind of stinks. My oven is broken, so hopefully it can be fixed before Christmas so that we can actually use it to cook good food for family. I'll let you know how it goes. I got kicked out of the living room, because, my family is out there now. My daughter's running around, my parents are here, and it's not conducive to doing a recording. Hopefully the last recording wasn't too bad with my daughter in the background, but now, yeah. There's actually a lot of other people that are up and about. So, let's continue today. We actually finished 7.1 the other day, so normally I would do, some homework questions here, but those will have to wait till I get back. But we should be able to finish 7.2 today. And we're gonna be a little ambitious. We're gonna try to finish all of 7.2. I think it's doable. Anyways. So let's get started. 7.2 is about the sampling distributions of proportions. So in relation to P, in relation to the proportion or probability of something happening, or the chance that we, the amount, or you could say, the proportion of people, or proportion of whatever it is, that we're looking at. So we're looking at, in relation to P, the population parameter P, the sampling distribution of that, okay, of P. And obviously the estimator of that would be P hat, right? That's the statistic. So, real quickly, an example, that we've been using in the videos was when I had that huge deck of cards, the population parameter P, would be the proportion of red cards within the deck, the true proportion of red cards within the large deck. And when I took a sample out of that, the 20 cards, whatever this proportion of the sample was, that would be P hat. So we're looking at the sampling distribution of proportions. That's what we're looking at today. Okay. So here are our objectives. We want to be able to find the mean and standard deviation of the sampling distribution of a sample proportion. We want to determine whether or not it's appropriate to use the normal approximation to calculate probabilities involving the sample proportion. And we want to calculate probabilities involving the sample proportion. And we want to be able to evaluate a claim about a population proportion using the sampling distribution of the sample proportion. Okay, I know that doesn't sound that clear right now, but by the end of the lesson, you should be able to do all of these things. And I will clarify all of them as we go throughout the lesson. But you should be able to find the mean and standard deviation. You should be able to determine whether a normal approximation can be used. And you should be able to calculate some probabilities involving the proportions, and you want to be able to make an evaluation about a certain claim that is being made about the population proportion P to see whether it's, reasonable or not. That's what we're looking at today. Okay, so let's look at some sampling distributions of P. How good is my P hat at estimating P? Now, there are certain things that we already know about this. So if we take a look at the sample the sampling distribution on the left versus the sampling distribution on the right. The main thing that you should notice here is that the sample size here is 25 and the sample size here is 50. Now, my assumption is that the population of candies is going to be 0.45. Oh, they actually say it up here. Is 0.45. But I was making that assumption based off of this right here. So the mean of the sampling distribution is 0.45, which goes to show that both of these distributions are good, which means my p hat is an unbiased estimator for p. Okay? Now, which one is better? Well, I would say this one, because there's less variability. Since they're both unbiased, right, this one has less variability, right? And you'll notice that both of these are normal, okay, normal-ish. Now, that is not always going to be the case. Like, if I look at these two distributions, this, is not a great illustration, but if you look at this, now, if the proportion of, like, if I were to change p from 0.45 to 0.15, if I were to change p from 0.45 to 0.15, now this is referring to the proportion of orange candies within the Reese's Pieces. Yeah, I should have mentioned that earlier. I'm sorry, but this is gonna be the first take, and I'm probably just gonna roll with it, because it's kind of like when I'm in class. So yeah, I know it's not great. But the proportion p represents the proportion of orange candies within a machine, right? And so if I were to change that from 0.45 to 0.15, you'll notice that the sampling distributions look a little bit different, right? You'll notice that this one is slightly skewed to the right, with the smaller sample size, okay? And then this one is actually is normal. Now, why is that? Well, you might be able to, guess why that is, and it's because 0.45 is kind of close to 0, and you can't get a proportion or a sample that's below 0, right? So my sampling distribution is going to be slightly skewed to the right. This means it matters what my proportion is in order for my sampling distribution to be a good or unbiased sampling distribution, right? So this one is going to be slightly skewed to the right, as you notice here, which means, it's not exactly what we want it to be, because we want to be doing normal approximations on these, and we'll see why in a moment. Okay? Alright, so what we need to look at for sampling distributions, now this is back to socks, right? So you want to look at the shape, center, and spread of them, right? We want to notice, like, for the sampling distribution, we want it to be normal, okay? Because that's the only thing we know how to work with. We want the shape to be normal. We want the center to be at P, right? Because it makes it an unbiased estimator. And then we want the standard deviation to be as small as possible. So in other words, as n gets larger, my standard deviation gets smaller. Now, again, there's, caveats to this, and we'll talk about that in a moment as well. All right, so how is p hat calculated? Well, p hat is calculated by taking the number of successes within my sample and dividing by the size of the sample. So in other words, x over n. That is how p hat is calculated, right? Now, if I want to look at the distribution of all of the possibilities of all of the possible p hats, I'm going to have to look, or if I want to calculate np hat, I am going to have to look at the distribution as a whole. Now, see if you can follow me here, okay? This scenario, or these scenarios, are actually binomial if you think about it, right? Success or failure, they're independent with the caveat of the 10% rule. So we have to check the 10% rule here. Okay? Remember, we don't really care if a scenario is not binomial. We don't really care whether a scenario is not binomial, as long as the 10% rule holds, because technically it's still okay. It's like a pretty good estimator of the scenario. So independence, as long as the 10% rule holds, then we're okay. And the number of trials is set at n, right? And the success rate is close enough to the same because my population is so big, right? The same thing as the 10% rule. So based off of that, our expected value, remember, within a binomial scenario, is just n times p, right? And so if I take n times p, that's my expected number of successes, right? And I want to find, okay, well, what is the proportion of success? Then I would just divide my mean of that scenario by n. And so then what you'll notice here is this goes with what I've been saying all along about our sampling distributions, is the case that my p right here, if I divide by n, which is going to get my my proportion of successes, right? That is just the proportion of the population, which means p hat is an unbiased estimator of p. I don't know why it says or, but yeah, of p. Now, for standard deviation, if I multiply the mean by the constant 1 over n, then I also have to multiply the standard deviation by that same constant. Right? And then when I do my calculations, here is my here's my standard deviation for my proportions. Okay, so if it's related to p, if I'm looking at the population parameter p, the mean of all of my possible proportions of p hats is going to just be p, and the standard deviation is just going to be p times 1 minus p hat, 1 minus p over n square root. Now, something that I want to point out here is the fact that this is more evidence that as n increases, the spread decreases, right? If my population is bigger, then my variability is going to be smaller. Okay. So, it can be summarized as follows. My mean of my sampling distribution is just p. My standard deviation is the square root of p times 1 minus p over n, as long as the 10% condition holds. Remember, because this is in relation to a binomial scenario, right? And also, I forgot to mention this. In order to do normal calculations on this, right? Because remember, binomial scenarios, as n gets larger, they become closer and closer to normal. So if we want to do any normal calculations on it, the n times p is greater than or equal to 10, and n times 1 minus p must also be greater than or equal to 10. These are all conditions that feed off of the assumption that the scenario is binomial. Okay, so when we come back, we are going to do an example. So I will see you in a bit.